few classes we shall discuss about the some terminology what we are talking about. So yesterday we had discussion about the enantiomer and then configuration and confirmation and other things, mirror image, handedness, so many other things we have discussed. So in that one, I would like to emphasize little bit more about the confirmation and configuration. That is over almost, but as a just I will repeat what we have discussed yesterday. Let me share my slide. Okay. So I was talking about the configuration and confirmation, and yesterday we talked about the enantiomer, how enantiomer is originating, and what is the polarimeter, and how this reading is coming out. All the things we have discussed, and enantiomer, I will just remind you. So yesterday we were discussing about the enantiomer. Enantiomer, I talked about the first we discussed about the chiral system. Chiral is coming from hand. Hand has a property of handedness, and these are the non-superimposable. So both hands are mirror image, and both has a handedness property. So the definition of enantiomer will be the non-superimposable mirror image that I talked about yesterday, and they have a property of the handedness, and such compounds are then chiral, similar to that one. And what is chiral? When compound is like a carbon has is attached to four different groups, and if you take a mirror image of this one, so 1, 2, 3, 4, they are not superimposable with each other. Yesterday I have shown with the models also. And this is the one enantiomer, this is other enantiomer. We talked about the properties of the enantiomer also. They have all the physical properties, boiling point, refractive index, other freezing points, other things are the same, but their property towards the plane of polarized light is different. Like this will, if it is rotating in the plus direction, this will rotate in a minus direction, and then you have a magnitude will remain same. If it is 10 degree, then also this will be the 10 degree. This is the thing, and its reaction towards the optically active compound means, suppose one enantiomer is reacting with the some protein. This is the some protein is there, structure is there. So its rate of reaction of this one will be different, and this will be different towards the this protein structure, because protein is a chiral. So its reaction with the chiral compounds is different. And because you cannot convert just by rotation this to this one, these are the two different configuration. Okay, these are the configurational isomer. So you have already studied about the conformational isomer, where you take a bond and just rotate it. Yesterday I talked about like a butane, you have studied ethane, you have a clicks form, you have lots of forms, intermediate forms are there, and two extreme positions are there. So that is just you are getting by just like this is the thing, and if you are rotating in this way, this is the eclipsed one. And if you rotate this one bond, you can have a other one, staggered form. So here you are getting the two forms, eclipsed and staggered, just by rotation around C single bond. See, but this configuration, like if you want to change this one just by rotating any bond, like here, and if you think you can convert to this one, that is impossible. And to convert, you have to break the bond, and then you have to bond breaking and bond formation, we can say. So this thing should occur, then only you can get the other enantiomer. Okay, is that clear? This much? So I hope I am clear, because I am just repeating is both again and again, because lots of people are getting confused here in during the exam. So
Yes.
whatever the weak point I am getting from your side, I am trying to reduce your mistakes what you are trying to do in exam. Okay, and sometimes I will show how to, like, this is the 1 2 3 4. Okay, when this is in 2D form, and this is called, there are different ways to represent the chiral compound over the 2D sheets. This is one. This is called Fisher projection. Other one is there, you must have seen, you can represent with the solid bond, you have to represent with the wedge bond. So these are the two different solid and wedge. These only we will talk about here, because others, if you are talking about others one, it will be very difficult to understand you, and it will make you just confused and complicated. So what sometimes I used to do, I rotate this one. Like, this is the tetrahedral form. I rotate this one. I can make, if you rotate this in this way, like take this one, rotate in this way, the fourth will go towards the, so third will come here, two will come here, and fourth will go here, one is remaining same. So I am giving these two structures and ask you what is the relation between A and B. So I am just rotating here. So rotation will not change the configuration. You are telling this is a different molecule, this is different. No, this A is equal to B. When I am breaking the bond here, I am just exchanging. Like, what you do here, I will just write here. One, oh, I will exchange the 3 and 4. 1, 2 will remain same, and fourth I am putting here, third I am exchanging here. So single exchange means you are breaking this first bond, and then third and fourth you are exchanging. Means now this is the enantiomer. Okay, just rotation. So you have to do some exercise to get the, because that is the in mind, you have to rotate it, and you have to see whether this molecule is same. Other way also is there, that we shall talk about by the nomenclature also, you can distinguish this molecule is same. So if it is just by rotation, those are same molecules, or we call them homo means same, mer means different molecule, homomers, the relation between the, or similar, or the homomers, not the enantiomer. They have a relation of the enantiomer. So this was, so here I was talking about how to represent the compound. So representing the compound means representing, and then how, based on the experimental value, how it is behaving. Like, it is rotating the light in right clockwise direction, you have to write small d in bracket, that is italic also, and, or the plus you can write. If it is like anti-clockwise, you have to write minus in bracket, and here. And suppose I am asking, if plus is one enantiomer, then what we can represent the other enantiomer by what sign here? If you take the mirror image of this one, how can you represent you? Just a common sense question. This is the plus enantiomer. So how to represent the other one?
Minus.
Yes. So this is the way. If I am representing here the D, then you can represent here the. So there, because when we will talk about the plane of symmetry, then there is a one example will come. Then you have to. It will make you easy to understand. So what we talked about till now, the importance we have talked about. Chirality we have talked about. Chiral center, mirror image, plane of polarized light, polarimeter, configuration and conformation, as well as the enantiomer. Okay, these are the topics we have covered till now. And furthermore, we have talked about the.
So you talk about homomers. Can you explain it again?
Okay. What are the homomers? Homomers generally what I will put put on my video and take out the model, then you will understand. So yesterday I have shown you such models. Okay, this is the model. Center is the carbon. You can assume, and four different white, yellow, this like sky blue and red color is there. Four different groups are there. What I talked about homomer, you just represent this compound. Suppose you can view this compound from your side. I think you can view the this one, the sky blue and yellow from towards you, and red is towards me. Okay, I am just rotating this compound. Okay, now red and sky blue is with you, and yellow is towards me. Again, I am rotating this one. Now red and yellow is with you, and sky blue is. You are not changing the molecule here. You are just rotating around single bond. So all the forms you can see are the homomers. When you are representing in a 2D sheets, just your rotation, it's like you can hold like this also. This also the same molecule. This also is the same molecule. This also is the same molecule. So in any way you can hold it and you can represent it, but you are representing the same compound. So different forms are there, different views are there. So what view you are seeing, that is important. But all molecules are same. That are called homomers. Is that clear?
Yes. See
Okay.
it like a conformer.
Yeah, it's no, not conformer. It's like a different view, different angle you are seeing the same molecule.
Means the identity of the compound will be same even after rotation in
Yeah,
homomers, na?
even with the rotation, you just rotate it here. It is same, but this is the confirmation. But you can hold from here also. You can hold
Yes,
from.
sir.
So in any, if you are holding
Sir,
through.
in conformers, the rotation identity of the molecule changed after rotation, na? In conformers.
Yeah, that is being changed, but here this molecules remain same. Okay.
Because it's a homomer, na?
Yeah,
Okay, sir.
homomers means you are the same molecule. You are representing a different way. Okay, there is a no
Okay, sir.
eclipse or no that thing is not there. That is staggered. Other things will be not there. Just your viewing angle is being changed here. Like this one is there. This is there. This is there. You can see. Like this is tetrahedral structure, 3D structure. So it depends upon from where I am seeing and from other side you are seeing. Okay, so angle is same, angle is different, but molecule is same. Okay, so you can make the same molecule from your angle. I can make the molecule from the my angle also, but this is the same molecule, right? So both the representation, what you are drawing, what I am drawing, is remaining same. And then both are molecule are same, just representation is different. So both relation is of the homomers. Okay, and suppose now I am breaking a bond here, exchanging this one and doing like this one. And if we compare with the earlier one, now compound is no more same. Now it is the, because you have broke the bond and you have formed the bond. So now this is the enantiomer of this one, because one time break and bond formation is there. This is the thing. Now I talked about the enantiomer with the single chiral center. Now we shall talk about the enantiomer of the with the two chiral center. So here I have made a molecule already. This is the carbon attached to 1, 2, 3, and this whole group will act as a third for this one, for this carbon, and this also is attached to the 1, 2, 4, and this hole will attach the, suppose I'm right, third prime. Okay, not the C, only the carbon. This whole group will act as a one atom here, like third substituent. Okay, so it has a two chiral center. I told that chiral center is being represented by the star. If you put a star, it means that is the chiral center or chiral carbon is there. If you take a mirror image of this one, so 2 will come here, 1 will come here, 4 will come, and this 4, 2, 1, like that one. And what happens now? The relation between this and this is of what? These are the mirror image.
So in enantiomer.
Yes. So if mirror image is of the chiral center are called enantiomer, they are not superimposable. So these are the enantiomers of each other. Now, what happens? This group you don't touch like this one. One possibility is there. Other group you just exchange here. You see, one is as the same place. I have exchanged 2 and 4, right? 2 is now this side, 2 is now. So we have changed the chirality at the one chiral carbon. Okay. Now the relation between this is not a mirror image now. Like 1, A, B, and C. So A and B are the enantiomer, but A and C are no more mirror image. Okay.
The diastereomers.
Yeah. So if they are not mirror image, so they are called the diastereomers. Okay. So relation between this also is a simple question. Suppose I am drawing this A, B, and C, and I ask you what is the relation between A, B, and C? Like what is the A and B? What is the A and C? So A and B is the enantiomer. What about A and C? You told it is the diastereomers. What about B and C? B to C relation.
Sir, meso, sir.
The
Meso
diastereomers.
compound.
Yeah, this also is a diastereo. This also are not mirror image because first group is remain same. Only I am changing the bottom one. So this also is the diastereomers. So what is the property of the diastereomers? So definition of the diastereomers are stereoisomer that are not mirror image. They are different compound with different physical properties. So there are other examples of diastereomers also. There one we talked about. All the geometrical isomer. We shall talk about detail in geometrical isomer, but we shall just because diastereomers we are talking about. So relation between the geometrical isomer is of the diastereomeric. Okay. So two enantiomers are chemically identical, but they are mirror image of one each other. Types of this one, all the geometrical, like if fumaric acid is there, malic acid is there, they have a relation of the diastereomeric relation there. And then next one is there, and when you see the properties of the diastereomers, so like an enantiomer, it is not like all the physical and chemical properties are different. They have a different boiling point, they have a different freezing point, they have a different refractive index, they have a different chemical properties, they have their interaction with the optically active compound is all different. Everything is different, unlike the enantiomer. And there are suppose I have shown you the model, but problem is there you cannot play with this model over the 2D sheets. So there are different ways are there to represent that molecule over the 2D sheet. That is a Weiss formula that I talked about, the solid bond, wedge bond, Fischer projection, Newman projection, flying wedge. This we shall not discuss much about this one. We will concentrate our things here over these two, wedge formula and Fisher projection formula. So, okay, here only I will talk about the wedge projection and Fisher projection. So, what is the wedge projection here? It is this is the way you are representing, and 1, 2, 3, 4. But now it is not clear which is on the back side, which is on the front side. It's not very clear here. So what do we do here? We take one as a one axis, like 1, 2 in a plane. We shall take 1 and 2. This is in the plane. So other things we shall take in a one outside the plane and one means behind the plane and front the plane. So behind the plane means we shall use to represent with the broken bond, and towards you means outside the plane. This is towards you. This is 3 and this is the 4. So I will show you here. So what this way, these things you have to represent in the 2D sheets. Okay. So what is the thing? Now you have to choose any axis that is in the one plane you have to decide. So I am deciding this white towards black and through black to the this color, ocean blue. Okay. This plane I am deciding. You got, this is the plane, and now this red is towards you and this yellow is on the back side of this plane. You see, this is the plane, and now this one is the plane you have decided, and one is towards you, red is towards you, and yellow is towards me, means back side of the plane. So this red one you will represent with the solid one because it is towards you, and this yellow is back side of the plane that you have to represent by the broken band. That's what I am talking about here. So I was talking about the rotation. I have decided this one, this plane white through black to the ocean blue. I will rotate this one. You rotate once. Now this is the ocean. Now you make the plane of the this one, white, black and yellow, right? This is the same molecule, but now this ocean blue is towards you and red is towards back side of the plane. Okay. So now the same molecule here, how we were representing it. Now if we take about the similar one, if you rotate it towards this one, okay, now this was the plane. Now 4 will come at the place of the 2 because I was talking about this one. Okay, so what was the back? If you are rotating back means yellow was the back, black back. Now this comes in the plane. So here, so back will comes in the plane means 1 and 4. 1 and 4 will the plane. Okay. So what was the front? That will go to the back. That was in the plane. That will come to the front. So 2 will come to the front and 3 will go to the back. Okay. So same thing like this compound you are representing in this way also. That's what I was talking about. Means you are representing the same compound in a different way. So further you can rotate this one. So you will get another one. Further you can rotate, you will get another one. If you are holding this axis, you can get another one. So all the compounds are remaining same. That's why I am talking about these are the all are relation of the homomers. Okay, this was the flying wedge representation. I was talking about how to represent in this way. Now I will tell how to make a Fisher projection to this one from this 3D bond. So now that also is little difficult to understand. Sometimes it is not possible. So this Fisher projection, Fisher has devised some different way, different method. Fisher was the name of the scientist. and he was a great scientist, especially in case of sugars. Sugars glucose structure you must have heard. It's a big structures, lots of chiral centers are there. So how to represent? You cannot represent so many chiral center over like this one, and this many people will confuse. So you have to make more simple way. This is the thing we talked about. So now what you have to do, you have to just rotate like this. Now, so two atoms are towards you, two atoms are towards me. Now you press it. Press means like this in the plane. You make it flat. Okay? Like this. So it was like that one 2D towards two atom towards you and two atom towards me, and make it flat here. Just press it over it, it will flat. So it was like that. I will draw here. This is towards you. This atom is towards you. And this atom is on the back side. And make it flat. So this whatever atom is on the this axis, this will become the vertical, and this become the horizontal. So if you make it flat structure like this, if it is like this one, if you make it flat structure like this one, so there will be one vertical line, one horizontal line. That's what we are representing here. So what is towards you, that will become the horizontal line, and what is perpendicular to that one, that is away from you, that will be the vertical line. Representing is 1, 2, 3, 4. It means this 2 and 3 were towards you, and 1 and 4 were away from you.
Sir, we have to press both the bonds towards us and
Yes.
towards you also.
Yes. Otherwise, you have to make it flat. So you have to. It's like you put like this one in this one, this plane, and put a pressure here. So you make it flat. Total out of this 3D, you have to make it flat. Now you can see me a little bit, right?
Yes.
So yellow and white will be the on vertical line, and this ocean green and the red will be the on the horizontal line. Right? So this is the representation of the, this is how it is being represented in the Fisher projection. So in our other things I told about, you have to choose one axis, and other one will be towards you, other will be the back side. And now this rotate like this one, something like this one. So one position will come like this one, right? Two bonds will be towards you, and two bond will be the back side of you, means towards me. Now you apply force from your side here. So I will write here, apply force from this side, right? Make it flat. So whatever
Yes,
on
sir.
the back side, that will become the vertical line, okay? And whatever towards you, that will become the horizontal line. That's what I am talking about. You can do practice there at your home also, with take some pen or some potato or something. You can make, and then in class I used to give to the student here. They can do, you can do the practice here, though you can understand in a better way, but online I think this is the best way. And sometimes you can get some animation also. Now you know how to represent the Wedge formula, how to represent the Fisher projection formula. So Fisher projection we are representing in this way. 1, 2, 3, 4. Here also you can rotate the atom, but I will tell how to rotate and what is the impact of rotation. So this is towards you, and this is the back side. So this is over, and then we shall talk about the symmetry element. Symmetry elements are certain elements of symmetry that decides the whether compound will be chiral or not. There are three symmetry elements we shall discuss about here. That is, one is the plane of symmetry, and other is the center of symmetry. And so I was talking about the symmetry elements. So three symmetry elements are there: plane of symmetry, center of symmetry, and alternating axis of symmetry. So planar symmetry is the any imaginary plane inside the molecule that divides the molecule into equal and opposite half. Okay. So In case of a structure with a plane of symmetry is achiral, if this plane of any symmetry element is present in your compound, that will be achiral, means that will be not optically active and superimposable on its mirror image and cannot exist as a two enantiomer. The structure without plane of symmetry is chiral and not superimposable on me. That's opposite to that first sentence. I will talk about here, like I made 1, 2, 3, and like 3, 2, 1, right? If this molecule has no plane of symmetry, but what I will do here, I will delete, I will just exchange here 2 and 3. Now if you imagine here, if there is a plane in this molecule that is dividing in molecule in just equal half here, like mirror image 2 to 2, 3 to 3, and 1 to 1. Okay, just mirror image up to that one. So if such molecules with the plane of symmetry are not optically active, okay, how it is not optically active? And because I will talk about the mesoform also, when such things are cancelling each other internally and how it is happening, that we will devise by the RS nomenclature, that there we can understand in a better way. I will not talk about the mesoform here. So, but such molecules are having the plane of symmetry and those molecules are not optically active. This is very simple, not much complicated. So we shall move towards the next one example, that is the center of symmetry. And center of symmetry means in molecule, if there is a one center and if you pass through any line, okay, in this direction, and if you extend in other direction, if you are getting the same molecule or atom, like this this H also, and this H also. In opposite way, if you are getting the same atom here, if you see here NH, CO, CO, H, CS3, CS3. So this molecule is having also center of symmetry, but this molecule, just I exchange SCS3 to CS3H, you are getting here, but here there is no, we are not getting the same. Here is the CS3, here is the H. Similarly, this also. Means if there is a molecule there is a center of symmetry, then on extending that line, you will get the same atom or same molecule or the same group of atom, then you will have a center of symmetry. And if you have a center of symmetry, then again molecule is optically inactive. Am I clear about this plane of symmetry and center of symmetry?
So center of symmetry, then object will be optically inactive, na?
Yes. Any
Okay, sir.
plane of symmetry, if it is present in molecule, either out of three, plane of symmetry, center of symmetry, or alternating axis of symmetry, then it is the optically inactive. Symmetry element decide whether your compound will be the optically active or inactive. And now we had one operation and one observation till now. This alternating axis of symmetry will have two operations here. Two operations means there is a rotation and reflection. Okay. So definition is there. A molecule possesses an n-fold alternating axis of symmetry. We talked about plane, we talked about center. Now we are talking about the axis here. When rotated through an angle of 360 by n, this is the arm, like this quadrangle 360 by n. If you divided by this, will come the 90 degree. If it is like a triangle, so 360 by 3, so it will come the 120. So pentagon is there. Similarly, you can decide hexagon is there. So based on that one, you can decide the degree. So 360 by n about its axis, and then followed by reflection. Reflection means you have to make a mirror image of this one. in a plane perpendicular to that. So first your action is the rotation. So rotation is there 360 by n degree, and this is the first one, and second was is the reflection perpendicular to the whatever you have rotated. So I have made a one imaginary molecule. So let's try to understand this one through this molecule. So this is 1, 2, 3, 4 tetramethyl cyclo, like butane is there. Don't tell this as other symmetry elements that I know, but this is not a real example. This is an imaginary example I have made to make you understand. Then we will go to the real example. What you have to do, this is CH3, CH3H, this alternate changes there. So you choose one axis, like this is there. This axis we have to selected. We have to rotate this 90 degree. 90 degree rotation means this 4 will come here, 1 will go here, 2 will go here, and 3 will come here. Means whatever now this has come here, CH3H, this HCH3 can go here, like that everything has changed. And this is the axis, or perpendicular to this one will be the this plane. You have to put mirror in this plane. Okay, suppose this quadrangle is the mirror.
So where we have to put the mirror?
Here, perpendicular to that axis. This is the axis, and then you have to put a mirror here. Like you can imagine this is the mirror. Okay, and then after mirror you have to make a structure. What is the, that is the reflection. So mirror, if you are putting this plane, so CH3 will go on the top and H will come on the bottom, right? Here similarly CH3 on the top will go to the bottom and H will go on the top. Here also this will go on the top and this will come on the, this CH3 come on the bottom. Okay, so you have done the rotation and then you have done the reflection perpendicular to the that axis. So two operations you have done, and this is the A, this is the B, and this is the
So
C.
can you please extend this once again?
Yeah, I will explain it because other examples are also there. Okay, so this was the molecule.
Okay.
You understand? Okay, this was the molecule. You have chosen one axis here, rotated through 360 by n, that is 90 degree. So this 3 will go here, 4 will go here. 1 will go here, 2 will go here. So whatever is moving, you have to make that structure here now. So once you make that structure, then perpendicular to that axis, you have to put the mirror here. Okay, so you have to put mirror here. Mirror means this is the, suppose this is the mirror, and then this CH3, whatever you have to take the, make the mirror image of the whatever compound you are getting after putting mirror. Like enantiomer, you are talking about A to A prime, something like CH3 was on the bottom. So if you take the mirror image of this one, so CH3 will go on the top. So mirror image of H will go on the bottom. Mirror image of H here will go on the top. Similarly here CH3 will go on the bottom. Now it is clear? अच्छा ठीक है, मैं इसको फिर से एक्सप्लेन करूंगा, अभी आप इतने पे रहिए, ठीक है? So
Okay, sir.
now we have, after mirror you have A, B and C structure. Now you have to correlate between the initial and final. Okay, so if you see here, if you are getting the same A equal to C after these two operations, then compound will having the alternating axis of symmetry, right? So after this rotation and reflection, if you are getting the same compound as the original, this is the original and this is after the two operations. Say, see here at this place H and CH3, CH3 and H, H and CH3, CH3 and H, means this A is equal to C. If A is not equal to C, then the compound has no alternating axis of symmetry. But it is there. That's why this compound, what we had taken example, has a alternating axis of symmetry, and this is not optically active, right? This was the thing. A, B. I'm trying to write B, A, B, B, A, right? And through axis, you are rotating this one. Now after through 90 degree, rotating means it is, you will get the this type of structure. Now B, this will shift to here. Okay, after rotation. So instead of A on the top, here will be the B on the top. So it will change at the every point. Once it is changed, so everywhere it will changed. Is that clear up to here?
Yes, sir.
Okay. Then this was the axis, and then you have to do the reflection in the perpendicular to this one. Perpendicular to this one, this plane is the perpendicular to that axis. So you assume this is this as a mirror. Put a mirror here and make the structure what you are getting after that mirror. You are putting that mirror. So this A was on the bottom. The mirror of A will come here, right? And mirror of will B go to the bottom. Is that clear?
Yes, sir.
Okay. And similarly here, A will go on the bottom, B will come on the top. Here also, A will go on the top, will come on the bottom. Similarly here, B will go on the top, A will come on the bottom. Now this is the structure A, this is the structure B, this is the structure C. You have to correlate between the structure A and C. If A is equal to C, then this molecule is having the alternating axis of symmetry. Here, see here on this particular side, A is on the top, B in the bottom, right? Here B on the top, A is on the bottom. Here A is on the top, B on the bottom. Here B is on the top, A on the bottom. Okay. So this was the thing, you know, and this A is equal to C. That's why molecule is having alternating axis of symmetry. Then molecule is not optically active. There is one more example, means real example will there, that I will talk about in your text class. Now it is 1 o'clock. So I will stop here. I have to take attendance also. So this real examples I will talk about the next class. I think Saturday is the Monday timetable, right?
Yes, sir.
So Monday means Saturday we are not going to meet. Then we shall meet again on the Tuesday.